Hi, today we are going to talk about buffer overflow attack. We are going to have a buffer overflow attack, and for this I have a vulnerable code like this, which is getting an argument from command line, and I have a buffer for which I have kept the size as 500, and I'm copying the argument which I got from the command line to this buffer, and I'm just printing the buffer. So by buffer overflow attack we mean we are going to give an input, an argument which is greater than this buffer size, so that it will reach the return address. So I'm going to demonstrate that now. So before that I open my command line. Okay, here first. Okay, for this my first I will disable ASLR, and the command for this is sudo sysdel, this the one which is on the screen, and I am going to allow my p traces also, and this is the command. Now I am going to compile my code. For that I am using a gcc -g world.c, and world is my object file, and I am using a flag fno stack protector. This is to disable stack protection flag which is present in Linux, and I am also using the command -z stack. This is to make the stack executable. Okay, so now now using gdb I'm going to debug this code. So gdb, my object file world, and for this I have gdb-peda installed. So from this we can see list. This is my code, and in using peda there is this command set arg hello. This will set my argument for the program as hello, and we can see that here, show arg. This will show my argument, and now I will run this. As expected, I can see my buffer printed. Now we will try to insert some junk. Okay, let it be is more than the allowed, which is 500. Since I am using a 64-bit machine, my instruction size is 16-bit, so there will be a 12 bytes of my instruction size would be 16 bytes, so there will be a 12 bytes of padding, and also there is an 8-bit of base pointer size. So that will be 512 plus 8, that is 520. So my overflow will be after this 520. We can check that. See, when I run this, you can see when I give 520, there's segmentation fault. So now we have to see where our return address will be. For that I'll just give 522 and check. When I run, see, I can see my 2 bytes have changed, so that means there is 6 bytes. So 6 bytes of address, so that will be 526. So let's see. Yeah, so I can see that my address is replaced by 641 provided by me, which segmentation fault is received. And this is the advantage of peda. We can see all the code, the stack, and the registers, and as you can see, my base pointer is AAA 4141, which is provided by us. Now so we understood that after 520 I have my address. So what for the attack, what I'm trying to do is I'll be adding a shell code, and then I'll be adding some random h90s corresponding to NOPs, and I'll be adding some NOPs and shell code and a return address here, a return address, and this return address will be pointing back to this NOPs. So I'll show that. First of all, we'll get a shell code from net. I'm getting a shell code from net, which this shell code is for spawning a shell. So I'll copy it. See, I'll copy this in my terminal. This is a 27 byte shell code. Okay, this is 27 byte shell code, and here I'll be giving my return address. So okay, since we don't know the return address for now, we'll give some junk values. 1 2 3 4. And I wish to repeat this 10 times. So this is like 60 plus 27, so that is like 87. So that will, the address will be like 526 minus 87, and that will be 439. So this will be working like, okay, there will be 439 h90s and a 27 byte shell code. That will together make it shell code and a 60 bytes of information, like 60 byte of address. So what we are going to do is we are actually going to give a return address here where this 90s will be, so that when we are going to so that whenever we give some input, this return address will be somewhere pointing to the NOPs. So this program will go back to this NOPs, and they will execute from there, and they will also execute the shell code which is provided by us, and we will not be seeing any segmentation fault as we had seen before. And as of now we don't know the size, as of now we don't know the address. That is why I have given some value like a here. Now we will run. This is bound to get a segmentation fault since we don't know what is there in the return address provided by us, 41 41 41 41 41. Now when I run, we can see that return address was made as 41 41 41 as expected, the one which was given by us. Now to see the memory, we will give this command. This is like I am getting 200 words from stack pointer minus the offset value, which is 500. So stack pointer minus offset value, from that position I am seeing 200 words of my memory. So let's see that. See, as okay, we can see that our 9090s are placed here. So our return address should be somewhere pointing to this 90s. So when we see the, okay, for randomly we'll take DE6C now. So okay, DE6C, since this is following a Little Indian format, we'll give 6C DE FF 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 and 7F. Okay, so So now this is like there will be 439 90s 27 bit of our shell code and 60 the address spreading. So in the last 6 bytes, in the end the last 6 byte will be our address, and this will be replaced in the memory. We'll run this code. As you can see, our shell code has run and we did not get any segmentation fault. So the buffer overflow attack is done. Now if I type ls, I can see all the files in the current directory.